Okay, so we are going to talk about the gas laws today. There are three main gas laws, and Avogadro kind of has another gas law, but really there's three main gas laws. We're going to talk about them again. But before we start, first of all, what factors do you think affect gases? Like pressure. We looked at the simulation yesterday. Pressure, what else? Volume, and temperature. Those are the three main factors that kind of affect how gases behave. So temperature, pressure, volume, and the one we kind of looked at yesterday, but it wasn't one that we were altering, was the amount. Or what do we know of what do we actually call the amount? What is the more correct scientific chemistry name for amount? Avogadro. Moles. So when we're talking about the amount, we're honestly talking about how many moles. Because can you actually sit there and count 200 atoms? No, but we can calculate a mole, right? Apparently, I did not finish my thought on this slide. The amount of the gas, practically. Amount or moles of molecules or whatever substance we're dealing with, what gas we're dealing with. All right, so let's just jump right into the first law. The first law is Boyle's law, named after Boyle, who came up with the concept. This law deals with pressure and volume, and they are inversely related at a constant temperature. So under Boyle's law, your temperature has to stay the same. Okay, if temperature stays the same, pressure and volume have an inverse relationship. What does that mean? If one goes up, the other goes down. So if our pressure increases, our volume is going to decrease. Okay, if everything else stays the same, but somehow pressure and volume are changing, they have to be going in the opposite way. And one way to write this is to write PV equals K. So what in the world is K, right? K is any constant, whatever we're dealing with. So we're not really going to be, it's not like K is a value, but for right now we're just kind of using K as kind of like a placeholder. Okay, it's a placeholder. So in a minute we're going to talk about initial versus final, what happens before, what happens after. But for right now, K is just a constant where it's holding a place. Okay, so Boyle's law, the actual equation for Boyle's law is P1, V1, the pressure at initially times the volume initially is going to equal the pressure in the final state times the volume in the final state. So again, it's a ratio. The law of conservation, right? It's a ratio. If pressure goes up this amount, then the volume has to go down in the same amount. Okay, as one goes up, the other goes down. So basically, we are going to let's try to graph this. So if we are graphing, okay, what do you think is going to go on the y-axis versus what's going to go on the x-axis? Remember, independent goes on the x, dependent goes on the y. So where do you think is going to go where? Well, what do you think is dependent on what? Volume is dependent, and your pressure is going to be independent. Okay, pressure, the only way we can change the pressure is if we, sorry, I got distracted. They're doing something weird out there. If our pressure, in order to keep pressure the same, our volume is going to have to go up and down. Okay, so if we were going to draw a line, remember this is inversely. As one goes up, the other goes down. How am I going to draw this? Okay, it's going to go
on top to bottom.
Like that? Okay, now in a perfect world, we would have a nice, pretty straight line. But do you think we have a nice, pretty straight line? No, it actually looks more like this. But we can still see it starts off high, it goes low. And I'm sure I could really explain to you how we derive it, but you don't really want to know that, do you? All right, so you guys ready to do a few examples? All right, so example 1. Okay, if we have 20.5 liters of nitrogen at 25 degrees Celsius and 742 torrs are compressed to 9.8 atmospheres at constant temperature, what is the new volume? So first of all, what piece of information can I just throw out? Nope. Temperature. Why can I throw out the temperature? It's constant. This is not going to affect anything, so let's just pretend it's not there. The next problem. What's the next problem? No. Yeah, the temperature is held constant, so it's going to be the same on each side, so we just throw it out. The next problem is one pressure is in torr, one is in atmospheres. So it honestly doesn't matter which one you convert. I think I actually converted the atmospheres to torrs. I don't know why I chose to do that one, but I did. So let's see here. Let's do 9.8 atmospheres. I decided to do this one to torrs. I don't know why. I just picked one. Okay, does anyone remember the conversion factor to go from atmospheres to torrs? You're right. Mercury, and one millimeter of mercury is 1 torr, so we can do 760 torrs. And I actually didn't do this step, I did this all in one step. So 9.8 times 760 gives us 7,448 torrs. Okay, so now I can use my equation. So what equation? We have pressure volume, right? So we're going to be using Boyle's law, which says PV equals PV. All right, so our initial pressure was 742. And it's really important. Usually we don't always put our units in the math, but in the gas laws, it's a good habit to get under because units become very important when you're doing these equations, and it's a good way to catch when our units don't match up, okay? So then we're going to times it by our volume, which is 20.5 liters. This is going to equal our second pressure, which we just found to be 7,448 torrs. And we're going to times that by our second volume, because that is what we were solving for, right? So then we do the fun math. We're going to do 742 times 20.5, and then we're going to divide it by 7,448 to get a volume of 2.0 liters. So, let's see, does this make sense? It's almost the exact same. Dilution was MV equals MV, right? Same basic concept. Let's see if this makes sense. So, what happened to our pressure? We started at 742, we rose to 748. Our pressure got bigger, so our volume should get smaller. Did it? Yes. Did it get significantly smaller? Yes. Why? Because the pressure got significantly bigger. All right, so let's do another example. All right, example 2. 30.6 milliliters of carbon dioxide at 740 torrs is expanded at constant temperature to 750 milliliters. What is the final pressure in kPa? Okay, so honestly what I would do is I'm just going to go ahead and use PV equals PV, and I'm going to get my pressure, and then I'm going to try to convert, as opposed to trying to convert first. That's how I did it. That's what makes sense to me. It really doesn't matter which way you do it. So we're going to do PV equals PV, and on this test, I am going to, if you do not, you guys have gotten kind of lazy over the last couple tests and you don't write your equations down, which has been okay, but this time around you have to write your equations because we're going to learn 4 or 5 different gas laws. So the only way I know that you know what gas law you're using is if you write the equation. Okay? So my first pressure was 740 torr. My first volume was 30.6 milliliters. My second pressure is what we're solving for, and my second volume was 750 milliliters. Solve for P. We get an answer of 30.192 torrs. So let's see, does this make sense? What happened to our volume? It increased by a lot. It went from 30 to 750, right? Didn't our volume go from 30 to 750? So what should happen to our pressure? Should go down. Did it go down? By a lot? Yes. So Yay, it makes sense, but now we need to convert to kPa because that's what it asked us to. So we need a conversion factor. Anyone know what the conversion factor is? 760 torrs is equal to 1 atmosphere, right?
Yes.
Okay. But we don't want atmospheres. 1 atmosphere is equal to what?
101.325.
Now, could we have done this in one conversion factor? Yes, but it's a little hard for us to sometimes make all of those jumps because we would have had to make the assumption of 1 millimeter of mercury in 1 torr. We would have had to make that assumption, and we would have had to make the assumption of atmospheres. So sometimes it's easier just to break it down into 2 steps. All right, and then we just need to do the math, and we should get an answer of 4. And since I feel like this unit is a little bit easier, okay, than we've done in the past, I am going to count for significant figures. Okay, I've kind of let you guys slide on those last couple of units too, just because the calculations have been so complicated. But how many significant figures does 30.6 have? What about 740? About 750? So my answer should have 2. So when you get your answer in your calculator, make sure you're doing the rounding correctly, okay? All right, so let's move on to the next law. The next law is called Charles' law. Okay, this time around we are dealing with constant pressure. So Boyle's law is constant temp. Charles' law is dealing with constant pressure. So what Charles' law says is the volume of a gas varies directly with the temperature. What does that mean? As one increases, the other increases. Okay, so as one goes up, the other goes up. As one goes down, the other goes down, which makes sense. You guys did the simulation yesterday. What happened to the volume as our temperature went up? It increased. In order to keep the pressure the same, if the temperature went up, the volume had to go up. And this says pressure has to stay the same. Okay, so very, very, very important, and I want you guys to write this in like capital, maybe star it, circle it, something. Our temperature has to be in kelvins. Why? Because we can't have negative numbers. Okay, the only unit or the only system that lets us do temperature with no negatives is Kelvin, so we have to do kelvins. Okay, how do we go from Celsius to Kelvin? Add 273. So the equation for Charles' law is V1 over T1 equals V2 over T2. Okay, so these are directly proportional. So if I had you guys make a graph, volume, temperature, directly proportional, what do you think it's going to look like? Probably more like, but as one goes up, the others go up, so it should be an increasing line, right? Sorry. Okay, so I'm sure you guys have all wondered about absolute zero. Absolute zero is this theoretical point in which everything stops moving, right? Have we ever gone to absolute zero? No, but we know it exists somehow, and this is actually how. So if we take the graphs of several different elements, so we have helium, we have methane, we have water, and we have hydrogen, we have all of these in the gas form. If you notice, they all meet at the exact same spot, right? Okay, that is negative 273 degrees Celsius, which is 0 Kelvin, which is absolute zero. So this is how we know that absolute zero exists. This is how we know that it does happen, but we've just never actually seen it happen. But because of looking at these graphs, looking at what all of these, because like for instance, maybe we could measure to this point. Maybe we can't measure the temperature any lower down than that. Maybe it doesn't exist there. But if we look at all this data up here, we have enough points plotted that we could continue the line. You guys have all done graphs before where maybe we've only done calculations up to 10 minutes, but it asks you to guesstimate what 15 minutes is going to be, and you just extend the line. This is kind of going in the reverse. So if we know the temperatures are like this, you put the ruler down, and you can see if we keep going, well, if you do that for every line, they all had a common spot right here. And so that is how we defined absolute zero. Not that it actually exists there, but that's how we define it. All right, so let's do an example. All right, so what would the final volume be if 247 milliliters of gas at 22 degrees Celsius is heated to 98 degrees Celsius? So everything's in the same unit except what? We are not in Kelvin. Uh-oh. So we're going to have to do a little converting ahead of time. But honestly, what I do is I just do that in my calculation. So we have V over T equals V over T, right? So my first volume was 247. So I just write 22 plus 273. We're solving for our second volume, and then 98 plus 273. Now, this is where we see how good we are at our basic algebra skills. Sometimes we get a little rusty on how to, you can cross multiply if you want to, but the most common mistake is when we're trying to solve for something in the denominator, which luckily this time around we're not, but we'll do that in the next example. Don't mess up on your simple algebra stuff here, okay, because it's really easy to make a mistake. So now we have to do, basically what I'm going to do is I'm going to do 247 divided by 295, because this is 295, right? Okay, and then I'm going to multiply that by 271, or 371, right? So my volume is going to equal 310 milliliters. So now, let's make sure this makes sense. What happened to our temperature? It increased. So what should happen to our volume? Did it? Yes. All right, so let's do another example. Hopefully this time around we're solving for temperature, which we are. All right, so we're going to be using the same formula, V over T equals V over T. This time it says what temperature would 40.5 liters of gas at 23.4 degrees Celsius have a volume of 81.0 at constant pressure? Okay, so this time, first of all, we're not in Kelvin. Secondly, we're solving for temperature this time, so we're going to have to be testing our algebra skills a little bit here, right? So let's fill in. So initially we had 40.5. Okay, 23.4, how do I convert that to kelvins? We add 273, so that gives me 296.4. Our second volume was 81 liters, and we are solving for our second temperature. Okay, so for some reason when we do these types of math problems, the initial thought is for you guys to move the number. You want to move the number to the other side, right? That's the initial, what everybody wants to do initially. They want to, and they do the opposite usually. They know that we need to divide here, right? But then what always happens is they forget that t is technically still in the denominator, correct? So the easier way, what I always tell you to do is get t on the other side. We don't want t in the bottom of a fraction. That makes math hard. That means we have to remember reciprocals and all that fun stuff. So get t out of the bottom. Okay. Move t to the other side. So I'm going to move t up here with the 40.5. And then we can see what we need to do, right? What do we need to do then? I'm going to do 40.5 divided by 296.4. And then what do? And then I move that answer, 81 divided by whatever we just found. Okay? So the answer here is going to be, our temperature is going to be equal to 593 Kelvin. So let's see, does this make sense? What happened to our volume? It went up, so what should happen to our temperature? Did it go up? Yep.
Well, whether it be when dealing with the volume and temperature will the ratio by which we multiply it or whatever, will that be equal with each of the change?
No, not necessarily.
I know, because I was thinking about that.
Within the laws, yes. But volume and pressure, I honestly, yes. I'll go with yes. Because we could, in a second, we're going to do a combined gas law, and we're going to put them all together.
Isn't 81 twice as much as 40.5?
Yeah, it should be, because they're all just direct. They're just directly and indirectly. They should be direct proportions. But there's probably an example out there that doesn't work like that. So I don't want to say. All right, so let's talk about Avogadro's law just a little bit. Avogadro, again, moles. He came up with the number 6.02 times 10 to the 23rd molecules in 1 mole of anything, right? He said that equal volumes of gases at the same temperature and pressure contain equal number of molecules. So in other words, 1 mole, or 6.02 times 10 to the 23rd molecules of any gas at the same temperature and the same pressure should equal 22.4 liters. Huh? We've used this before. Why? Because we did this unit in general chemistry. Okay, so at constant temperature and pressure, the volume of gas is directly related to the number of moles. So this is going to look very similar to Charles' law that we just did. And because Charles' law said V over T equals V over T. Avogadro's law says V over N equals V over N. So it's basically the same thing. It's direct proportion. As one goes up, the other goes up. As one goes down, the other goes down. Okay, we're actually not going to do an example of this. Why? Because it's the exact same that we just did. It's just this time we're going to have molecules instead of temperature. But same basic type of equation. Which makes sense. The more moles you have, the more space you should occupy, right? These are directly proportional as well. All right, so the third gas law is Gay-Lussac's law. I know, funny name. Okay, at constant volume, so let's see here. Boyle's law was constant temperature. Boyle's law was constant. All right, Charles' law was constant pressure, and so now we're at Gay-Lussac's law, in which we have constant volume. Okay, so whatever variable is not in the equation is the one that's held constant. Does that make sense? Okay. So these, what do you think these are going to be? Are these directly proportional or indirectly proportional? Directly proportional. As my pressure goes up, so should my temperature. So think about it. If we have a container, think about the simulation we did yesterday. There was a box on the screen, right? So if my box cannot change, my volume is being held constant, my box is not expanding, but my temperature is going up, what does the pressure have to do? It has to go up. Because as my temperature goes up, my molecules are moving faster and faster and faster. The faster they move, the more collisions they have. The more collisions you have, the higher your pressure. So as the temperature goes up, the pressure goes up. The only way that pressure would not go up if temperature was going up is if our container was allowed to expand. This is why things explode when you leave them in the car in the middle of summer. This is why soda cans explode. This is why if you leave like aerosols, I don't know, whether it be hairspray or deodorant or whatever, in your car in the summertime, and in your car it can go all the way up to over 100 degrees in a day. Okay, that is why sometimes those types of things explode.
We had a perfume more all of a sudden I had the bottle. Any precise
Mm-hmm.
like a few days ago, I actually from the shower, it exploded.
Yes, any pressurized. Alrighty, so let's do. Now, if we take all three of these laws and we put them together, we get a really creative law called the combined gas law. We're combining the three gas laws. So let's just, really quick, we had Boyle's law, which says PV equals PV. We then had Charles' law, which said P over T. Is it P or V? P. And then we have, right? Boyles, Charles, and Gay-Lussac's. So we have these three. Now, if we take these three laws and we kind of shove them all together, okay, we will get this. So we can use this if nothing is held constant. If our pressure is changing and our volume is changing and our temperature is changing, which honestly is what's going to happen in the real world, correct? Usually temperature is not going to be held 100% constant. Usually pressure can, I mean, most bottles or boxes or whatever, they can expand to some degree before they explode, right? So volume isn't necessarily going to be held constant. Pressure definitely isn't going to be held constant very often. So this is the law we're going to use most often. So let's do an example of this law. Yes?
Is that why, like, soda or when you buy water, it's not filled all the way up?
Mm-hmm. So you have just a little bit of room for expanding. All right, so let's look at example 5. Example 5 says a deodorant can, so we're talking about exactly that. Deodorant can has a volume of 175 milliliters and a pressure of 3.8 atms at 22 degrees Celsius. What would the pressure be if the can was heated to 100 degrees Celsius?
So, even though this is the combined, will we need to have this in Kelvin?
Yes. When you're doing gas laws, our temperature always has to be in Kelvin because technically we're using that law where we have to convert them all to Kelvin. Okay. So, the hardest part about using the combined gas law is you have 6 variables. You have to remember which ones go with the initial and which ones go with the final. And so you guys have seen me do this before. I underline initials and I circle finals. Okay? So we have a deodorant can that it starts off with 175 milliliters, starts off with a pressure of 3.8 atms, and it starts off with a temperature of 22 degrees Celsius. And it is going to end with 100 degrees Celsius, and we are going to be solving for pressure. Now, we're missing something. We're missing our second volume. This is a deodorant can. We're going to assume it's the same because you guys have seen a deodorant can. Is it going to change volume in your car in the back seat? It'll expand to some degree, but for the most part, we're just going to assume for right now that the volume's going to stay the same. Okay? All right. So now we're going to use,
So could
we could technically use the other equation, but we're going to use the combined gas law.
so we could just not use volume?
All right, so pressure, 3.8, times our volume, which is 175, times our temperature, which is 22, plus 273, which equals 295. 295 is going to equal my pressure. My volume is going to stay the same. And my temperature is now going to be 373.
So like on the test, if it doesn't give us a second volume, should we just assume that it's the same?
Yes, but I probably will give you one a little bit more straightforward. All right, so again, there's lots of different ways you can solve this. You can cross multiply if you want. You can I used algebra. I didn't think to cross multiply, but you can cross multiply. Anyhow, we need to get PL by itself, right? After you do the fun math in whichever orientation you want to, we should get a final pressure of 4.8 atmospheres. So, we started at 3.8. We're ending at 4.8. What's the difference between 3.8 and 4.8? 1. So let's just think about this. 1 atmosphere is the pressure at sea level of the entire Earth pushing down on the surface. That is how much the pressure is increasing in one tiny can of deodorant. That's a lot. That's the amount of pressure pushing down on the Earth at sea level. So that is why leaving stuff in your car over the summer can be bad, because if that were to explode, it's going to come out of there with a lot of pressure, and your car is a lot smaller of area than the entire Earth, right? So it's going to make it. That's why sometimes things can cause harm. That's why some people get hurt just by leaving stuff in your car. Because that doesn't sound like a lot of pressure, but it is. Okay? All right, so let's do another example. We're actually going to use this same data for another example. Same basic process. Okay, so for example 6, it says, what volume of gas could the can release at 22 degrees Celsius at 743 torrs? So we're going to use the same initials that we had a second ago. But this time, what's being held constant? So temperature. So let's not use the combined gas law this time around. Let's use a different gas law. What gas law could we use? If our temperature is starting at 22 and ending at 22, our temperature is held constant. So what gas law could we use this go around? Boyle's, which says what? PV equals PV. So our initial pressure was 3.8. Our initial volume was 175. Uh-oh. This time we are in torrs and not atmospheres, right? So, since I've actually already started my problem, I'm just going to do this. I'm going to do 700. I'm just going to add my conversion factor right into here. And then again, however you want to do fun math, right? There's lots of different ways you can do this. My volume is going to equal 680 milliliters. So let's take a second. Does this make sense? What happened to my volume? It went up. Now, we can't really see what happened to our pressure because one's in atmospheres and one's in torrs, but 743 divided by 760 is probably going to give you an answer smaller than 1. So what happened to our pressure? It went down. So 1 went down, 1 went up. Makes sense, right? Alrighty. So I want you guys to go ahead. I have some example problems for you. I want you to go ahead and get started on assignment 1. We don't have a lot of time in class, but you can probably get 1 or 2 problems done just to see kind of where we stand.